And let's move on the next speaker. That's Tom Veeken from AMOLF, who will talk about directing emission of quantum dots soft stamped on silicon Mie resonators. The floor is yours.
Thank you, Katarina. Also, thank you for inviting me to give this talk. My name is Tom Veeken. I'm a PhD student in Albert Pommes Group at AMOLF. And before I start, I would like to thank all the collaborators on this project. Benjamin, Harshal, Mark, Esther, Eric, Bruno, and also Albert. So the title is on directing emission of quantum dots. So why would we actually want to be able to direct the emission of quantum dots? Yes. There on this slide, I show a couple of examples. The first being a singlet fission solar cell. It's a little bit beyond the scope of this presentation to explain the dynamics of such a solar cell, but the organic material tetracene that you see here on top gets excited by light, and there are triplet-excitons that you would want to move into the silicon to do light conversion. That conversion is not so easy, so an option is to place quantum dots at this interface, move the triplet energy into the quantum dot, and make the quantum dot radiate downwards. That was the initial setup of this project, and so the objective of this quantum dot would be to radiate downwards, thus wanting directional emission. But the second option would be to think of a luminescent solar concentrator, which is composed of this thick transparent window, which includes quantum dots as luminophores. Sunlight is absorbed by these luminophores, and their objective is to emit in plane towards a solar cell here on the side. And thus you would want directional emission in plane. And a third example that you could think of is that of a quantum dot LED, either for lighting or in a quantum dot television, where the quantum dot layer here is supposed to emit out of the device upwards. And not downwards into the device or in plane into the device. You want the light to couple out. So those would be objectives to do directional emission. And we started from the point of a singlet fission solar cell with a silicon substrate to see if we can use nanophotonics to increase this directional emission or control it. As a start, let's make a reference case, which then would be the silicon solar cell at the bottom, a dipole as modeling the quantum dot in air, and working at the 760 nanometer wavelength, because the quantum dots that we'll use in the experiment have the same emission wavelength peak. So we use first Green's functions calculations to calculate what the emission as a function of direction is for this dipole above the surface 5 nanometer away from the surface, and we find the result that you see here on the right, 93.5%, when we average over all three polarizations of the dipole, X, Y, and Z oriented. Please note the logarithmic scale on this angular plot, which is why we reached the high percentage already of 93.5%, which is mostly due to the dipole being very close to the silicon having the higher index in this system, and thus having a higher local density of states, therefore emitting downwards. So now we can change this system. We would, for instance, want to emit upwards or emit stronger downwards, closer to 100%. To this 100%, we can add the following nano cylinder underneath the dipole, and then optimize its shape, the diameter, and the height to find a maximum of 98%. Going to this nanostructure, we've moved from Green functions to FDTD simulations, because the Green's function cannot basically include such a nanostructure. And here we are using the Mie resonances, the local resonances in this nanostructure, so not any lattice resonance. Okay, how do we find this optimal structure leading to 98%? Well, we change in the simulation its diameter and its height in color. And then we look at the total downwards emission. And we see that for small diameters, we're strongly emitting upwards because the downwards emission is smaller than that of the reference case. And then we actually overshoot to 98% here. And then as the diameter becomes bigger, you can understand that the dipole starts to feel as if it is on a flat silicon substrate, and therefore it moves back to the 93% for longer diameters. All of these results on this page are for a single dipole in the center. So if we would place our dipoles, our quantum dots in the experiment only there, we are supposed to have these results as a function of diameter. But you could also think an experiment of covering the total top side of this cylinder, and then the results are a little bit different. We again perform all the FDTD simulations now for all quantum dot positions and averaging over them. And then we find that we can pretty finely control as the diameter increases what the extra enhanced emission upwards is away from the substrate. We don't reach a case where it is optimal for a singlet fission solar cell, but it would be optimal for the opposite figure of merit, which is for the LED coupling upwards. Okay, with these results showing that we can alter the emission of dipoles or quantum dots on nanophotonic structures, we went ahead and fabricated those structures. We made cylinders in a square array of silicon on the silicon substrate, so etching down using e-beam lithography, and with an objective of 425 nanometer in this SEM case, we have nice cylinders with flat sidewalls. So with these cylinders, we can take the next step, which is printing quantum dots on top of them. We developed a soft stamping method where we use a PDMS stamp that is siliconized to decrease the adhesion of quantum dots. Then we spin coat about a monolayer of these quantum dots on its surface and turn it around to press it down on the nanostructured silicon. There we heat the silicon for about 10 minutes and then retract the PDMS stamp to facilitate only the quantum dot transfer on the cylinders where it actually touched with the PDMS and not in between, because the PDMS could not buckle in between this nano hole basically. As you will see later in the photoluminescence experiment, there are large amounts of flat silicon on the sides where the PDMS can buckle down and then print large areas of quantum dots. So then again, looking in SEM at our print, we see on the top surface of a single cylinder that there's conformal coverage and complete coverage. And also looking at our PDMS stamp, we see there are no quantum dots left. So we have a complete transfer of quantum dots. Good. With quantum dots on our cylinders, we can actually look at their emission. So we use a confocal microscope made by Veeken to make, as a function of position, the photoluminescence maps that you see on this slide for an array with a diameter of 200 nanometer or 425. And then here you see the change in emission, which is where the array stops, because here on the right side, there is the flat silicon reference case. So in a single measurement here, we can compare the flat silicon, 93.5% emission into the substrate, comparing it with the array, and doing the same for the 425 nanometer case. So now we want to know if we actually emit, as we predicted with FDTD simulations, stronger upwards or downwards for these diameters. To do so, we have to do one correction here, which is that the amount of quantum dots per unit area on the cylinder array is smaller than that of the flat silicon. We only printed on the silicon top size. Because the pitch is, in both cases, 3 times the diameter size, we have a factor of 11.25. So the emission of the array is actually higher than of the silicon if you consider a single quantum dot emission. But that is what we see here in this figure, comparing measurements with simulations. Because we normalize in simulations and in these measurements to the flat silicon case, that becomes a flat line at 1. And then on the y-axis here, we have the upwards emission, showing about 6 for the 200 nanometer case, this measurement, and then about 2.5 for the 425 nanometer case. The blue line shows the simulated upwards emission that we would expect, also normalized to the flat case in the FDTD simulations. And we see that the measurements line up perfectly with this trend. For this simulation for on cylinder, we have also made a correction, which is that the excitation efficiency of a quantum dot by the 532 nanometer laser is actually enhanced due to the cylinder array. So we calculate what is the enhancement of this, the field intensity of the laser at the array, and we correct for it to obtain this blue curve. And then we find that the measurements actually show the same trend. Then there is a final thing that we can look at to figure out if our simulations actually predict what happens in the measurements, and that is not looking at the lifetime, not looking at the PL intensity, but at the photoluminescence lifetime. Seen here, for the same two arrays, 200 nanometer diameter and 425 nanometer diameter, we look at the time traces. This is the short lifetime, the shortest component, and we normalize to 1. And then there is an obvious difference between the two arrays. In the 200 nanometer case, there is a faster lifetime on the cylinders, and in the 425 nanometer case, it's roughly the same. So we fit these traces to extract the lifetimes, and then we compare them to the same simulations that we did for the intensity mapping. Then we normalize again here to the flat case, becomes 1, and we have the blue line showing an oscillation of the lifetime. This basically shows that as we change the cylinders that we use, the nanophotonic cylinders, we change the local density of states that the quantum dots feel, thus oscillating as a function of diameter, because we have different resonances in the cylinder as a function of its diameter. Again, here the black circles show the measured results of these two figures on the left, showing lower PL lifetime for the 200 nanometer case and roughly the same for the 425. And that also coincides with the predicted results from simulations. So with that, I would like to conclude. I hope I've shown you that quantum dots can be coupled to these nano cylinders, which act as Mie resonators. And by coupling them, we can direct their emission. We developed a soft stamping method to print these quantum dots only on the silicon top surfaces. And then using photoluminescence mapping of both the intensity and the lifetime, we show that the direction of emission and the lifetime of its emission is perfectly predicted by the FDTD simulations. Thank you for your attention, and I'm happy to take any questions.
Thank you very much for your really exciting talk. So before somebody posts a question in the chat, I will again ask my questions. You said that the PDMS soft stamp is buckling or not buckling down. Would that depend also on spacing between the cylinders? I can assume if the cylinders are closer that there will be no buckling, and then you cannot deposit anything in between.
Yeah, it does seem to depend on the size. So here the distance is maximum 1.5 micron, as you can see from the SEM, and then it doesn't buckle in between. But I guess that if you go to tens of microns, then it does.
Mm-hmm. Okay, another question. So if I understand it correctly, you have some kind of diffraction, let's say a diffraction pattern from this scatterer. Which the light emitted from these quantum dots can be efficiently basically reflected from the surface or coupled to this Mie resonance. Is that can I call that Purcell effect, or is there some kind of enhanced coupling into the far field radiation through this diffraction?
Yeah, so the emission of these quantum dots is basically controlled by the Purcell effect. As you can see here in the third graph, there is the oscillation of the lifetime as a function of diameter. And there you're basically changing with the diameter the cavity that you think of with the Purcell effect. And as you change the cavity, you have different resonances, and thus the lifetime will move with this local density of states change.
Okay, so you could basically use this to measure radiative rate of materials. If you would make such pattern, sell it as a set of different sizes of cylinders, then people can deposit their nanoparticles and measure radiative lifetime.
I've never thought of that, but it might be possible actually, yes.
Sounds like I will buy that. Okay, there's a question. Did you measure radiation patterns and compare to simulations?
Yeah, so I think Freddie is asking about these kind of patterns, which you could maybe measure with the Fourier setup. And we have not tried that yet, but maybe we should just put it in a Fourier microscope and see if it aligns. Thanks for the question.
Okay. Yeah, I guess so. From your simulations and measurements, it seems that for LEDs we would need very small, let's say 200 nanometer cylinders, while for solar cells it has to be the larger flat surface, let's say. Do I understand it correctly, or? Yeah,
indeed. For the LEDs, you can use these type of cylinders to emit more strongly upwards.
Okay, and the size, let's say 200 nanometer, when it starts being more efficient, that would probably correspond to diffraction limit. Am I correct, or?
No, so the diffraction limit doesn't come into play here, I think.
Okay, so why would there be certain threshold size of 250, let's say, nanometer in diameter for the single dot?
So the change here in the left graph as a function of the diameter, that is due to different Mie resonances being present in the cylinder.
So coupling into the cylinder.
Being excited in the cylinder by a plane wave if you use it, or in this case by the dipole as an excitation.
Okay, so yeah, okay, I understand. Thank you very much. If no one else has a question, let's thank all the speakers from this session. And thank you all for coming here and listening to their presentations. Okay, I will close this session with thank you all.